Hey everybody, going to look at graphing tangent and cotangent functions. Already looked at sine and cosine, and then cosecant and secant. And so let's now then see what we can do here. So first let's remember what we've done. Let's graph one full period of this crazy function right here. So let's first do some simplification to this. Let's go to the inside here and let's factor it. So let's factor out that negative 3 and we'll be left with what? X plus something, but what is pi over 8 divided by 3? Well, it's the same as pi over 8 times 3, all in the denominator there. So 8 times 3 is 24, and so we're going to get plus pi over 24. That's a little messy, but it's okay. We can do it. Ain't no biggie. Let's figure out what our period is. Well, period's going to be the normal period for a secant function, which is the same as it is for a cosecant function, which is the same as it is for sine and cosine, which is 2 pi. Let's take that and let's divide it by that coefficient 3. And yes, I am dividing it by a positive 3, not a negative 3 there. You'll see why in a moment. But I get 2 pi over 3 as the length of my period, which is kind of messy, but it's okay. I'll recognize that 2 pi over 3 is the same as 16 pi over 24. That might come in handy when we sketch this. So let's draw our axes like that. I'm going to label this right here as the length of the period, which is 2 pi over 3. I'm going to label the halfway point as half of that, which is going to be pi over 3. And I'm going to label the halfway point as half of that, which is going to be pi over 6. And so then this spot right here is going to be 3 pi over 6. But if you think about my phase shift, I'm going pi over 24 to the left. So let's figure out how many pi over 6's go into pi over 24. Or I guess I should say that the other way around. How many pi over 24's go into pi over 6? And really what we're saying is, what is pi over 6 divided by pi over 24? Well, notice that's going to simplify to 6 over 24, which is 1 over 4, which means that pi over 24 is 1/4 of pi over 6. Long story short, what it's saying is, notice I'm going to make these big tick marks like that. What it's saying is that there are 4 little tick marks in each pi over 6, and one of those little tick marks equals pi over 24. Just splitting things up. So pretty helpful if you are comfortable using fractions. If not, this is probably a nightmarish problem for you. But if you are good with fractions, it's not really a big deal right there. Now, how about that pesky negative? So, secant is the reciprocal of which function? Secant is the reciprocal of the cosine function, and the cosine function is an even function, which means that the secant function is an even function, which means that that negative doesn't do anything. So I'm just going to straight up turn that into a positive 3, which is pretty cool. Then we have a negative 1/2 coefficient out front still. But before we even take any of that into account, we need to recognize that we have this transformation of +2, which is going to shift everything up by 2. So I'm going to move this down a little bit, like that, and I'm going to extend these axes up because I need to shift everything up by 2. So what I'm going to do is I'm going to draw in a little line of symmetry at the y value of 2. And if each of these tick marks represents 1, notice that our amplitude is 1/2. So we need a little half tick mark in between there because that's where our points will go. Alrighty then. Well, what do we do now? Cosine typically starts at its maximum value of 1, but we're multiplying it by -1/2. So this cosine graph would start at negative 1/2, but we're shifting it up 2, which means we need to start at 2 minus 1/2 which is 1.5. And also, we're being shifted to the left by pi over 24, which again is one of those tick marks. All of that together means I would get that point right there for my cosine function. And then I would just run through oscillating around about that line of symmetry. So my next point, which should be one little tick mark to the left of pi over 6, is going to be right there on that line of symmetry. My next point is then going to be up, and then my next point is going to be back down, and then my last point there is going to be below right there. But that would be if I were graphing cosine, and I'm graphing secant, which is the reciprocal. So remember what happens. The zeros turn into vertical asymptotes. Well, I don't have zeros anymore, but I do have those points that are on my line of symmetry. So those are all going to correspond, correspond to vertical asymptotes. And then what else do I know? Well, I know that the maximum and minimum values on the cosine graph will also be on the secant graph, except they will change. If it was a max, it's now a min, like this one right there. And if it was a min, it's now a max, relatively speaking, like that one right there and that one right there. So that right there is technically one full period of this secant graph. If it makes you uncomfortable to have just those little partials right there, we could split this up like that, and we could continue this down. Wait, where would that go? That doesn't look right. This would need to go past that tick mark right there. Boop, 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 boop. And we could do the same thing over here. We could increase this one out one more like that, and then we'd end up one left to it. So this one would come down like that. You don't need to do that. The other one's fine, but this one gives us a little more of the function, which is cool too. Now, what did each thing do? Well, each thing did a lot of different things combined. The -3, well, first off, we factored it out. It became a +3 because cosine is even. That's kind of cool. Then what happened? Well, we realized that that 3 was going to modify our period, so we took 2 pi and divided it by 3 to get that period of 2 pi over 3. And what else did it do? Well, that 3 also affected what our phase shift was, because we had to factor the 3 out of the pi over 8. More specifically, we had to factor the -3 out of the negative pi over 8, which changed it to a positive pi over 24, which then means my graph was shifted to the left, because it's plus pi over 24. That +2 shifted the line of symmetry up. The -1/2 did two things. It flipped my cosine function, aka it also flipped my secant function, and it also made the amplitude of the cosine function 1/2, which again corresponded to the minimum and maximums being closer together in the secant function. And you can kind of think of it as like a little amplitude right there, that distance between that point and the line of symmetry. So that's what all those pieces did. It's a lot all combined, but we have the knowledge and tools to handle all those different pieces. Okay, so that was tough, but we did it, and we did it with confidence. So now let's look at starting to look at graphing functions, namely tangent and cotangent. That was a very long way of saying we're going to graph some tangent and cotangent functions, and we're going to be smart about it just like we always are. We're going to use our prior knowledge. So in doing that, we need to figure out what the period of the tangent and cotangent functions is. Everything else was 2 pi. Maybe this will be the same. Maybe it'll be different. And then we want to apply some transformations to the mother function. So just as before we graphed secant and cosecant, we looked at a rational function. We're going to do the same thing here. We're going to jump back again to our polynomials and rational functions unit, and we're going to try and remember how to graph this. So to graph this, we need to factor it, which means we need to figure out what two numbers multiply to -28 and add to +3. Well, it's going to be a positive 7 so x plus 7, and a negative 4, because 7 times negative 4 is indeed negative 28, and 7 minus 4 is 3. So the numerator factors like that, and the denominator is a difference of cubes, which, I'm sorry, a difference of squares, which means it's going to factor as x plus 3 times x minus 3. And remember what the zeros in the numerator give us. So the zeros, aka what x values make those factors equal to 0. So in this case, x, whoa, where are we going? Where are we going? Here we go. X equals negative 7 and x equals positive 4 will correspond to zeros. When the numerator of a fraction is 0, the whole fraction is 0, and x equals plus or minus 3 will correspond to vertical asymptotes. When you have a 0 in the denominator, you get a vertical asymptote because you can't divide by 0. So let's sketch this in then. Let's go 1, 2, 3, 4, 5, 6, 7 right there should be a 0. And let's go 1, 2, 3, 4 should be another 0. And then we'll go positive 3 is a vertical asymptote, and negative 3 is a vertical asymptote as well. And so we need to figure out, where is this function positive, where is this function negative. So what I'm going to do is I'm going to pick a point, and I'm going to pick the easiest point I can think of to test to determine if that point is positive or negative. I'm going to test the point with the x value of 0. So if you plug in 0, 0 plus 7 is 7, and 7 times 0 minus 4, which is negative 4, is a negative number. That's all I care about. Numerator, I get a positive number times a negative number, divided by a positive number times a negative number. Those negatives will cancel each other out, and we'll be left with a positive number. What does that mean? That means that my graph has to be positive in this section right here, which means it has no choice but to look like that, because I don't have any zeros, so I can't cross there, and it has to be positive because we plugged in 0 and it was positive, and we don't cross. So there's that, which means if you look at the multiplicity of the zeros in the denominator there we have x minus 3 times x plus 4. Both of those vertical asymptotes right there that we're getting then are those factors both have a multiplicity of 1, which means the tails need to go to opposite sides. So I have to start down here, I have to hit that 0 and cross, and then I'm going to level out to the y value of 1 there. And same thing over here, have to be on the opposite side, have to cross, and then have to level out to 1. I should have a horizontal asymptote at the x value of 1 because I have x squared over x squared is 1. So it should look something like that. Key pieces to remember: when you get a 0 in the denominator, you get a vertical asymptote, and when you get a 0 in the numerator, you get a 0. So now let's figure out what this tangent function looks like. So what I'm going to do is what I've done in the past. I'm going to draw my axes. I'm going to put a tick mark there, and for now I'm just going to label that as 2 pi. I don't know yet what the period for tangent is, but that should give me something to start with. So label that pi over 2, and then 3 pi over 2 right there. Okay, well, the first question is, where does sine of theta on the interval 0 to 2 pi equal 0? Well, remember, sine is the y value, so it has a y value of 0 there and there. So at 0, pi, and then again at 2 pi. Well, why do we care about the zeros? Well, sine is the numerator, and that means then that the tangent function will be 0 at those values. So it needs to be 0 at 0, and it needs to be 0 at pi, and it needs to be 0 at 2 pi like that. And we know that from the sine graph anyways. Next question is, where does the cosine function equal 0 on that same interval? Well, cosine is x, and cosine is 0 when we're straight up and straight down like that. Well, those are going to be vertical asymptotes. And so I'm going to sketch those in at pi over 2 and 3 pi over 2. So, got my zeros, got my asymptotes, and last thing we need to think about is, where is tangent positive, where is tangent negative? Well, we can just think about all students take calculus. All students take calculus, just like that. Well, in the first quadrant, between 0 and pi over 2, all functions are positive, which means tangent has to be positive between 0 and pi over 2. Well, our only option is to curve up like that as we approach the asymptote. Okay, in the next quadrant, pi over 2 to pi, notice that only sine is positive, which means my tangent function has to be negative up to that 0. And again, I have to approach that asymptote and go to positive or negative infinity. Since it's negative, it has to be negative infinity. Well, what happens next? Next, I enter the third quadrant, pi to 3 pi over 2. Well, tangent is positive in that quadrant, so I'm going to curve up like that. And then finally, in the last quadrant, only cosine is positive, and that means tangent is negative, so I got to curve down like that. If you can picture what's happening here, we're getting this like kind of funky little graph that looks like that, and each one of those little down-up tails is a full period. Remember, a period is just saying how long does it take until you start to repeat. Well, in between each asymptote, tangent's going through a full cycle, which means that the period of this function is not pi, not 2 pi, but the period of the tangent function is just pi. And again, we can think of that as how long does it take to get back to where you repeated. Well, think about starting at 0 there. At this point, once we hit pi, the function repeats. It curves up to infinity, just like that. And so if you look here, we have 3 full cycles going on this graph, so we've shown 3 full periods of the tangent function. And think about why that makes sense. Tangent can be thought of as slope. Well, if you think about this angle right there, pi over 6, once you've gone around by a multiple of pi, you're back to that same line. That line has the same slope. And that's going to be the same case no matter what line you choose, whatever straight line through the origin that you choose to draw. You're always going to get one full pi around hits you back to that same line. So it makes sense that our function is just going to repeat itself after pi, versus the sine functions change. The sine and cosine pairs change. If you think about sine, well, think about sine right here. It goes from 1/2, then it goes up, and then it goes back down and hits 0, and then it goes negative, and then it goes back up to 0. And that takes a full revolution around the unit circle to hit that pattern. Up, down, down, up. But tangent only takes half of a revolution, so the period is pi. And just like every other function, if you look at throwing a coefficient in front of the tangent function, notice that the zeros will not change. The value of those vertical asymptotes will not change, because again, those do correspond to zeros, just zeros of the cosine function. But what happens? Well, it gets stretched. So if you have a fraction less than 1 in front of it, you're going to get a very squat tangent function like that pink one, versus the normal blue one there, or the stretched red one, and the even more stretched black one. They're getting kind of thinner and taller as you continue to multiply by a larger coefficient. And just like normal, if you were to make that a value negative, your graph would be flipped. So now, let's see how we can graph this one. Just like we did with sine and cosine, we want to factor the inside first, including negatives. So pull that negative out, we're left with x minus pi over 4. And since tangent is an odd function, just like sine, we can pull that negative out front. So we're going to think of this as the function negative tangent of x minus pi over 4. Notice there's no coefficient in front of the x, so my period is just a normal pi. I was about to write a 4 for some reason. My period is pi. So let's split this up. Let's label our period there as pi. But this time, since tangent goes through a full period in just half the unit circle, instead of putting 4 tick marks there, I'm just going to put 2 tick marks like that. But I do have my shift of pi over 4, so I will add that in. So I'll go halfway between each of these to get a pi over 4 and a 3 pi over 4, just like that. And we're shifting to the right. So let's now sketch in this function. Tangent normally goes like that, starting at its midpoint right there with its 0. But we are graphing a negative tangent, which means it's going to be flipped. So it's going to have to look like that instead. So instead of going up when it starts, it's going to go down and to the right when it starts. Let's sketch in our zeros. We know that every pi over 2, we're going to get a vertical asymptote. Again, think about the unit circle. We're saying anytime our tangent, our line is straight up and down, we're going to get a vertical asymptote. Well, that would normally happen at pi over 2 and 3 pi over 2, but everything is being shifted to the right by pi over 4, so instead of having a vertical asymptote at pi over 2, we need to have one at 3 pi over 4. So I'm going to dash that in there. We'll need another one, but we'll sketch that in a moment, because what do I know? I do know that my graph is going to start right there because of that minus pi over 4, and it has to go up. Whoop, that would be a positive tangent function, but we're doing a negative one, so it has to go down to the asymptote like that. Now, where do we go from here? Well, we could go forwards or we could go backwards. It really doesn't make a difference. I'm going to get another 0 right there, again corresponding to the two values where sine is 0. Normally that would be happening at 0 and pi, but now it's happening at pi over 4 and 5 pi over 4. And so I'm going to sketch in that bit right there. And technically that's a full period, even though it's an awkwardly disjoint period. To make it look a little bit better, I'm going to put this point over here so I can add an additional asymptote in like that. And now I can continue this graph backwards and up. And now we can see that it looks a little bit more like that tangent function there. So that's negative pi over 4 right there. And again, I could continue to draw these as long as I wanted to. I could extend this out if I wanted to and call this point right here, instead of pi going up again, that would be 3 pi over 2 right there. And then I could put myself one little more tick mark right there. To give me 7 pi over 4. Oops, that's a 5. 7 pi over 4, because this was 5 pi over 4 right there. And then I would be able to draw that next asymptote right there and continue that graph down like that. And now we can start to see that pattern of tangent a little bit better. And it is nice to see at least 2 of those there. Alright, let's do one more tangent graph real quick. Again, same process as we normally follow. Let's factor the inside there. So pull that pi out. What are we left with? We're left with x minus, x not, we can't talk, x minus 1/3 right there when you pull that pi out. And this is tan, and that's a 3 tan. There we go. Okay. So if our period is normally pi, we're dividing it by pi to get a period of length 1. So I will draw my axes out. I'm going to label this as a 1, and then I'm going to label this as a 1/2 right there. but I do have a phase shift of 1/3, which is kind of annoying because it's a little ugly. So what I'm going to do is I'm going to break this down a little bit more. I'm going to break each 1/2 down into 3 equal pieces because then each one will be 1/6, which means the second tick mark is 2/6, which is the same as 1/3. So again, you got to use fractions here. That's 1/6, that's 1/3, and that's 1/2. 1/6, 2/6, and 3/6. And then I can break this down as well. And what do we need to do from here? Well, we need to shift our graph 1/3 to the right. And so I know that my starting point is going to be right there. And then halfway through, I need to have a vertical asymptote. So that needs to be 2 tick marks to the right of 1/2. So I need to get that going down right there. And now I need to add some more tick marks to be able to really fill this out. So let's call this 2 right there. Is that long enough? I don't think it is. Let's call that 2. That's still not long enough. Let's go extend that. How about that? Is that good? I think that looks good. So that's 2. So there's 3/2, and now we'll split that up into our thirds like that. Because now I can put another 0, 2 tick marks to the right of that 1. So right there, like that. And I can put another vertical asymptote, 1 tick mark to the left of that point. So again, you really got to think in fractions for this stuff. So I'm going to start here at 1/3, and I'm going to curve up. Well, what does the 3 in front of the tangent do? It just kind of stretches it a little bit. So it's not going to get as much of a like curvy bit thing like that. It's going to be more like, whoa, I'm narrow. So then this is going to come down like that. There you go, that's there. And then this thing's going to come up like that. And where's that going to end? Well, again, that's going to end 2 tick marks to the right of that. We'll have another asymptote. And there you have it. There are 2 full cycles of that tangent graph right there. Okay, so now let's do the same exact thing to graph cotangent. Well, what is cotangent? Cotangent is defined as the reciprocal of tangent, which means instead of being sine over cosine, it is cosine of x over sine of x. So again, we're going to need to think about the unit circle here. It always comes back down to that. And so let's again label 2 pi, pi over 2, and 3 pi over 2. And now let's think about where we're going to have zeros. We're going to have zeros where cosine is equal to 0. Well, where's cosine equal to 0? Straight up and straight down. So at pi over 2 and at 3 pi over 2, we will have zeros. Where are we going to have asymptotes? Well, we're going to have asymptotes wherever sine is equal to 0. Where's that? Right there at 0, right there at pi, and then again at 2 pi. So asymptote to start right there, asymptote in the middle, and asymptote at the end. And again, let's use all students take calculus to figure out if our graph should be positive or negative. Well, between 0 and pi over 2, everything's positive, which means so then is cotangent. So we have to go like that. Boom. And then it's going to repeat that same exact pattern. Boom. And that is the basic shape of cotangent. Compare that to tangent. Tangent had asymptotes offset from that, like that. And tangent had its first value 0, and it went up like that. And then it went up like that. and then it went up like that. So look at how they're similar, look at how they're different. Pretty similar, but looks like their curves are going in opposite directions. And notice where one has a vertical asymptote, the other has a 0. So that's kind of cool, but unconfuse us a little bit. This is our cotangent graph right there. It looks pretty good. Okay, so let's go ahead and factor this. So cotan of 1/2 times x plus 1/2. All right, that means that we're going to be shifting this graph to the left by 1/2. What's our period? Well, the period is going to be pi divided by that coefficient, which is 1/2, meaning pi divided by 1/2 is the same as 2 pi. So this time we're going to have a longer period, so I'm going to call this 2 pi right there. And remember that the cotangent and tangent functions, they go through half their cycle in half of the 2 pi. So I'm going to be shifting everything to the left. Sorry, not by 1/2, but that should say pi over 2, and that should be pi over 2. So I need to give myself a pi over 2. So if these big ticks are my pi's, and there's a pi over 2, and there's a pi over 2, and there's another one. So cotangent's first point is actually going to be an asymptote. That's what we saw a moment ago. And then each half cycle it will get a 0, and then full cycle it will end with another asymptote. So tangent starts with a 0, ends with a 0. Cotangent starts with an asymptote and ends with an asymptote. And they both start positive. So if I have my 0 halfway through, this graph is going to have to look like that. Boom. And we're done. But what did I do? I goofed everything up because we shifted everything by pi over 2 to the left. So that asymptote should be there, not at 2 pi, but at 3 pi over 2. And my halfway point where I have a 0 should be there. And now I can sketch it in, and that should look a lot more symmetrical.